Exercise 2D is applications of differentiation. Now, that should sound quite familiar. You've already looked at applications of differentiation. Why do we differentiate? We differentiate to get an expression for the first derivative, or differentiation expresses the rate of change of a variable. Or we might want to sketch a graph and we'll find the derivative to find stationary points, turning points on our graph. Or we might simply be asked, where is the function increasing? And we know that if we find the first derivative and we set it as a positive, then the function will be increasing in the range of x values that satisfy the first derivative greater than 0. So all those things you've done before. The only difference now is the function will have something to do with the exponential. Like in the previous exercise where you were practicing differentiation with the exponential, and you had to keep within the boundaries of the rules for differentiating, like function of a function, product rule, quotient rule. Now, in the applications, we'll still be doing the same things as we previously did in applications of differentiation. However, like I've just said, the function will commonly contain an e to the x. A couple of years ago I put together a little golden book, and I'll see if I can get that open. And as you can see, it's a PowerPoint display, and here we actually look at differentiation on the whole. And I think that now that we've got a couple of different methods for differentiating, then we can try to put it together. I won't go through the entire PowerPoint part. Let's see. Differentiation is all about rates of change. We can look at the rate of change of a polynomial function, or we can look at the rate of change of exponentials. This rate of change just means we're getting the first derivative. Eventually, we'll look at differentiating log function, and because we haven't done it yet, it's still in the grey, and of trig functions. And there are rules depending on how complicated the function is. You've got the product rule, the quotient rule, the function of a function rule. We looked at those last exercise, and now we're doing the applications. And that's the end of my little book. We will also go on and find the second derivative, because we also did that in applications of differentiation. And we know that we look at the second derivative to, again, get an idea of what the graph of the function, original function, is doing. And we know that second derivative tells us about concavity, so concave up, concave down. And like it says there, it's helpful in sketching complicated functions. Okay, I'll pause the video. You should have a read of example 1, and maybe pause the video as well, and I'll fill out the solution to this and then come back and talk about it. Okay, so in part A, you were asked to find the gradient of the tangent, and yeah, I'd forgotten about those very basic sort of first step questions that you got when you started differentiation. In that the derivative gives you the gradient of the tangent. So yeah, remember that we started off finding the equation of the tangent. So while this doesn't ask you to get the gradient of the equation of the tangent, it asks to get the gradient. And if you've had a read through, it's sort of stepping you through the processes to actually focus more on the normal. So we know that the normal has a gradient minus 1 over the gradient of the tangent. Then we're getting the equation of the normal, we're getting the y-intercept and x-intercept of the normal, and then we're finding the area of the triangle created by the normal, the x-axis, and the y-axis. So, yeah, simply to find the gradient, yes, we're just going to differentiate, and it'll be e to the minus x multiplied by minus 1. We were asked to find the actual gradient. Now that's the expression for the gradient. And we were asked to find the value of the gradient at the point minus 1e. So here's our expression for the gradient. It obviously depends on the x value. The x value at that point, p, is -1, x is -1. Subbing that in. Now, this is the sort of setting out that they were encouraging students to actually do. So write your dy dx, write when x is -1. And then the marker can actually see that you know you've got to substitute -1 into your gradient and actually show it. This is the other step they were saying. Tell the students to show every substitution, simply because it's really easy to make a mistake. And as we go through here, maybe you'll pick up that I've made a mistake, though I think I've been fairly careful. But I'm sure, yeah, you know, you've seen me make mistakes before. It's very easy to make a mistake. You don't want to be doing that in the HSC. It's very costly, very costly. You might think 1 mark here and there won't really matter, but that is certainly not the case. And every mistake you make will potentially make the question more difficult and will take you more time, and that will take away from the questions that you could be attempting, and yeah, potentially getting some marks elsewhere. So it's not just within this question that it costs you, it will potentially be elsewhere. So we're going to take a few seconds to write little things like this and get the correct answer. So we've got that the gradient at that point is -e. Now this was not asked, but at -e, that's about -2.718. Although this is not required, but it's interesting, what does this tell you about the graph of y equals e to the minus x? It's telling us that at this point we're going to get a negative gradient. Now, that's quite different to the graph of y equals e to the x. What do you know about the graph of y equals e to the x? It always has a positive gradient. So just think about that. What does it mean then for the graph of y equals e to the minus x? Now, if you've learnt those transformations of the exponential that I think I put in the first exercise we did here, which was 2b, then you will know that y equals e to the minus x. This graph actually does this. So it's actually good to know that, oh yes, that at this point down here at x is -1, I do expect to get a negative gradient. Each time you actually work something out, see if you can relate it to the graphical representation. And what is it telling you? What is this information that I'm working out algebraically? What is that telling me graphically? And if it makes sense, if it matches what you know, then you can feel quite confident that you're on the right track. B, so write down now the gradient of the normal. And this again is the setting out that you're being asked to practice and then actually produce in your HSC solutions. The gradient of the normal is equal to -1 over the gradient of the tangent. Therefore, the gradient of the normal would be -1 over, here's our gradient of our tangent, minus e, so it's -1 over minus e. And again, show that, put that in. It's easy for you to get it correct thereafter. Students who don't actually show this will often mess up minus 1 over the gradient. So we've got the gradient of the normal, and we probably have done enough of these by now to know that that's probably moving us on to getting the equation of the normal. So, yep, C is no surprise, hence determine the equation of this normal. And again, we're going to write out what we know. The equation of the normal, with this now as its gradient, passing through this point, will be in this general form. Y minus y1 is m times x minus x1. And again, the students that show this are more likely to substitute correctly in and get the correct equation. So y minus y1 is e. M, we've just worked that out, is 1 on e, and we've actually stated it here, so we're more likely to get it correct. X minus x1, well, x minus minus 1 is x plus 1. You can leave it in that form. Another common format for the equation of a straight line is your ax plus by plus c is equal to 0. So you might see this actually written as multiply everything by e, so it's e times y minus e squared is equal to then x plus 1, and so you may see the equation written as x, bring the minus ey over, add the e squared and plus 1. Either form is correct and acceptable. D. Now we've got the equation of the normal. It then goes on to say we'll find the x and the y intercepts of the normal. And again, good setting out, we'll have x intercepts occur when y is 0. And another reason to write it is it reinforces that concept for you. X intercepts occur when y is 0. Therefore, we've got our equation, and I stayed with the first equation and subbed y equals 0. So we have 0 minus e is 1 on e, x plus 1. And again, I've got that into an x value, because that's what we're finding, the x intercept. I want to know the x value. So I would make x the subject of that. And surprisingly, the markers were saying this simple algebra is where a lot of students came undone, wasted time, got lost, didn't get the marks. So please make sure you know that you're multiplying both sides by e to remove the fraction here, leaves you with x plus 1, making x the subject, even simple things like that. And even I noticed when I marked the HSC last year, and it was really simple algebra steps that students were making mistakes with, and we were instructed not to give a mark. Even though the student did know in that case what to do, we were instructed not to give the mark. So there will be at times there will be questions where there is no forgiving for a silly little mistake. So just be aware of it. Practice every question that you do between now and the HSC, setting out every step and being careful. The y-intercept occurs when x is 0, subbing x equal to 0. We want the y value, which is this 1 on e plus e. And you can always at any stage do what I did back here, which was just out of interest. Get an idea of where that would be. 1 on e, you know, is 1 on 2.7. Well, let's just say it's 1/3. Plus e is nearly 3. So it's going to be a bit over plus 3. Where's this? So we know that this normal would cut the y-axis at a bit over 3. This one, x, what does it mean, negative x, e squared minus 1. Well, let's say that e is 3, square it is 9, so it's negative 9. Subtract another one, we're down at about negative 10. Now, that is going to be helpful for the next question, which actually asks you to, how is it worded? Find the area of the triangle whose vertices lie at the intercepts, I think it really should say, of the normal and the origin. So at the intercepts, oh no, I think that's okay. Find the area of the triangle whose vertices lie at the intercepts and the origin. So this triangle has its vertices, its angles, at the intercepts and the origin. So I've actually drawn it here. Here is my normal. Here is the intercept. The y-intercept was this 1 on e plus e. The other intercept, the x-intercept, was this negative e squared minus 1. And obviously here's the origin. So we've got to get the area of this triangle. The area of a triangle is half its base times its perpendicular height. Now, the base is not negative. I'm sure if we drew a triangle here and it was down at negative 10 and it was up here at 5, you would know to call the base 10 units. You wouldn't call it negative 10. We're not going to call this negative, and it is actually negative e squared plus 1, taking the negative out. We're going to ignore the negative in terms of calculating the area, because the length of this is really this e squared plus 1. So you can see there I've got the base as e squared plus 1 and the perpendicular height. And again, Marcus would say this is where students come undone, just doing basic expanding brackets. Year 8 work, expanding brackets. So knowing that, you're probably like the students across the state, that it is highly likely that you could make a mistake under the pressure of an exam. Then take every step to prevent that from happening, which is write down every step in your working. And the answer, you might see this answer written as e plus e cubed on 2 plus, and then I've seen it written e to the minus 1 on 2. It is actually question 7 in exercise 2D from your textbook.